Okay, so today I'm gonna go over for 6.1. Okay, so 6.1 orthogonal set. So I'm gonna introduce a lot of terminologies and notations will be used to construct the SVD. Okay, and the orthogonal stuff. So first one, orthogonal set is the set of vector a set of vectors u1 through to un. Let me say p. Okay, this is in Rn space. Okay, so this set is said to be orthogonal set, means that the two of vectors are orthogonal, which means that is said to be set if ui dot uj is equal to 0. Okay, so here this is a dot product, or I mean, in vector calculus, that symbol means a dot product. Okay, but the linear algebra, normally we call that one as inner product. Okay, so pretty much this is a kind of new operator between the vectors. We saw that how to add the vectors, how to subtract vector from the vector. But how about the multiplication? So this is kind of the multiplication operator between vectors. Okay. So the definition of the dot product or inner product is simple. The ui dot uj is equal to, so let's say the ui is, this is a column vector. We can express any vector as column vector, right? The ui is a ui, oh, sorry, is a u1i, u2i, to the uni, okay, and then uj is u1j, u2j, to the nj. Okay. Then dot product of two column vectors is defined by the product of the sum of product of each pair of entries. So which means the sigma and then u ki times u kj, and the k goes 1 through the n. Okay, does it make sense? It's easy example. Let's say u1 is 1, 2, 3, and then u2 is minus 1, 0, 2. Then u1 dot product of u2 is equal to 1. 1 times negative 1 plus 2 times 0 plus 3 times 2. This is that. Okay, that's just multiplication. Okay, so the interesting is that the dot product of the two vectors return a scalar, not a vector. Okay, so when you do dot product of two vectors, then you should get a scalar, which means a real number, not a vector. Keep in mind this. So that's the definition of inner product. And then going back to the definition of orthogonal set. Okay, so this set is orthogonal set if a dot product of two vectors in that set returns 0 for any I and j. Okay, so for any I and j, but I and j two subscripts, the index in subscript must be distinct. Okay, all right. So here's theorems. Theorems 4. So if, okay, so let's say if the S the set of vectors, orthogonal UP, is an orthogonal set of non-zero vectors. Okay. So you said and okay, so it's a set of non-zero vectors in Rn space. Okay. Then S is linearly independent. So the first one. This is linearly independent, okay? So and hence the the S is a basis for the subspace. The image is just SUB SP, which stand for subspace, okay? SUB SP stand for subspace that's spanned by S, okay? So let me prove this. I mean, give me a second. Okay, let me prove theorem 4. The first statement, S is linearly independent. So starting from the definition of linearly independent is C1, I mean sigma and then Ci and the Ui. This is a vector. Sorry, this is vector. Okay. So I goes 1 through the P is equal to 0. In this, the linear combination, I mean, this equation involving linear combination of Ui. Okay. And I want to show, we need to show that this solution has only the solution Ci equals 0, right? So then we start from this. We multiply sigma I goes 1 through the P and Ci Ui times vector U1. We multiply it. We just multiply the vector U1 on both sides of that equation. Since this is U1, I mean 0 times U1, 0 times U1. But U1 times 0, 1 is what? 0, isn't it? Okay, but okay. So this is 0 vector, sorry. This is 0 vector. Okay. So that's the yeah. Actually, this should be in a second. U1 and transpose, right? Oh no. U1 how can I express this? I think it makes you confused. So let me just say 0 vector. So 0 vector means that we need to do left multiplication U1 by U1 on both sides. Okay. But 0 vector times, U1 vector is still U1, right? So now this is equal to the left hand, just figure out the left hand side. This is gonna be what? C1 times U1, right? U1, okay. And then times U1, okay. U1 right here. Okay. So here, dot product. This is dot product, okay. Dot product right here. Dot product. And then plus C2 times U2, dot product U2. Plus and the CP times UP, right? Dot product U. Okay. So I think this is dot product right here. Dot product. So keep in mind the dot product satisfies linearity. I think I should have mentioned this. So vector U dot vector V is equal V plus W is equal to U dot V plus U dot W. Okay. So now we got that's why we got this. And then also this dot product says by community property, which means that u dot v is equal to v dot u. Okay. And then the u dot v is equal to actually in matrix form is u and the transpose and then vector v. It makes sense, right? Okay. So keep in mind this one. All right, so that's why we got this one. U dot p right here. This is equal to 0 vector right here. Okay. Oh, now u1, sorry, this is a 0 vector right here. This is equal to 0, right? It's 0. Sorry. So now then the left-hand look at this. This is equal to C1 times U1 dot U1, right? Plus C2 times U2 dot U2 plus the CP times UP dot UP, right? Oh, this is U1, right? This is U1, sorry. So this is U1, U1, this is U1. Because the operator says by the community property, so we can swap the U1, U1, U2 and through the U1, UP. That's why we got this. But we assume that what? The set is orthogonal set, which means that U1, U2 must be 0. I mean, all of the dot product where the sub-index, the subscript distinct is 0. This is 0, this is 0. Okay. So now this is equal to 0 here. So what we got this C1 times U1 dot product U1 is equal to 0. Right? But we assume that what in the theorem, we assume that the U1 through UP are non-zero vector. So what C1 must be 0. So this U1, I mean UI is non-zero vector. Right? And the I goes 1 through the P. What? C1 must be 0. Okay. Similarly, we do this. C1, you do this. U2 dot and sigma I goes 1 through the P and then Ci UI equals 0. We set this, okay? And then through the what? Set UP dot sigma I goes 1 through the P and then Ci UI equals 0. Okay, by solving these equations, similarly, we're gonna get for this one, we're gonna get what? C2 must be 0 through the CP equals 0. Okay, so proof is done. I mean, the proof the proof of the first statement is done, right? Okay, and then next one, so we prove that the linear S is linearly independent, right? So then linearly independent set can be used as a basis, right? So the second statement is obviously true. So now we just we're gonna focus on the not just orthogonal set. We're gonna narrow down the uh the orthogonal set can be used as a function. This is called as a basis. That is called the orthogonal basis. So next one is all right. Here's the definition. That's a simple. So orthogonal basis is the orthogonal set. First one, orthogonal must be a orthogonal set. Okay, but this one that orthogonal set must be must span the subspace in Rn space. Okay, so on the orthogonal basis for a subspace W, which is in Rn, okay, is a basis for W. Is a basis. . W, okay. So that is also what? Orthogonal set. And so here's a theorem 5. So okay. So in theorem 4, we figured out that the U1 through UP are linearly independent, right? Okay. But now, when you think about orthogonal basis, all right, so when you express a vector belong to that subspace as a linear combination of that orthogonal basis, linear combination of vectors in the orthogonal basis, then how can you find out weight? That's a question. Okay. So what that means, let's say U1 through the UP. Okay. Okay. This is not only just orthogonal set, but also orthogonal, I mean, basis. Okay. That can span a subspace W. Okay. Let's be an basis for a subspace W of Rn. Okay. Then for each W, oh, Y, sorry, vector Y in Rn space, a W in the subspace W, then the weight in the linear combination, let's think about this, Y bar is equal to C1. Think about this, Y bar is in the subspace W, which means that we can we have to, you know, we can express Y bar as a linear combination of that vectors in the orthogonal basis, right? So C1 times U1 plus C2 times U2 through the what? CP times UP. Simply saying that this is sigma and the Ci and the Ui are, and the I equals 1 through the P, right? So here's cool. What is a Ci? Okay, let me use a J instead of I, okay? Uj, J, okay, yeah. So in theorem 5 says that Cj is Y dot Uj. This is dot product, okay? This is dot product over Uj or dot product with Uj. Okay, here J goes 1 through the P. So let me prove this. Okay, so here, let's see. Okay. So we're going to use the orthogonality of the orthogonal basis. Okay. So Y dot product, inner product of Y and U1 is equal to what? Is equal to Y, you know, from that equation, we just do dot product of U1 on both sides. This is similar to what we did in the previous theorem, right? Theorem 4. So Y dot U1 is equal to what? C1, I mean sigma, let me just sigma, and J goes 1 through the P, and then Cj in the Uj is, and in a product of U1, that is equal to C1 times U1 dot for U1, right? We did that. Why this is equal to this? Because, you know, U1, dot product U1 and Uj, and the J is not equal to 1, turns out to be 0, right? So that's why we got this. Okay. But all right. So we want to find out C1, right? So C1 is what? Because what dot product to return what? Scalar, right? So this is scalar, this is scalar. So we can divide this one by that, right? Then C1 is equal to Y dot product of y and u1, and then what? u1 and u1, dot product u1. Okay, right. And then u1 is a non-zero vector, right? So you don't have to worry about the denominator turns out equals 0. Because orthonormal basis, we assume that what? This guy is orthonormal basis, which means that u1 through up are non-zero vector. Okay. So, all right. So denominator is defined for any define, okay? Don't worry about that. And then yeah, C1 is this. And similarly, what? U y bar dot and then u2 is equal to the sigma and then cj and then uj, and then j goes 1 through the p, and then top of u2 is equal to what? C2 and then u2 dot of u2. So C2 is what? Y dot product to u2 over u2 dot u2. So yeah, in general, what CJ is what? CJ gonna be Y bar dot product to uj, right? Over uj dot uj. Okay. So yeah, that's why this is how to find out this. What does that mean here? What does that mean? This one. So okay. Uh we want to figure out the geometrical meaning of uh the dot product. And then we to do that, we want to express the vector for given vector y with a vector u, and and then we do want to express y as a linear combination of vector u and other vectors. But the magnitude of y will be adjusted. Okay, so that I just multiply by alpha. So we're gonna express y as alpha u plus a w. Here w must be equal to eventually equal to y minus alpha u. Y minus alpha u. Yeah. So then 0 times to figure out, and then we're gonna find out alpha. Let's find out alpha. 0. Sorry. Then y minus the, give me a second. Let's say here the w was what? This is y minus pi by u, right? Okay. So then here, then what? The y minus the r by u. This is orthogonal. That is orthogonal to u, right? If and only if that symbol means orthogonal, okay? That means what? 0 times what? 0 is y minus alpha u times a dot product of u is equal to 0. The left hand side is equal to what? Y dot u minus alpha u dot vector u. Okay. So now then this is equal to yeah, that is equal to 0. So alpha is what? Y dot u over u dot u. So algebraically, yeah, I just figured out alpha, or you can say the what? Using the theorem 5, the alpha must be equal to what? Y dot u over u dot u. You can say that, but either one just fine. Okay. So this is orthogonal if and only if alpha is equal to this. That's why if you set alpha as this fraction, I mean this one, this is equal to this. Okay. Alpha we set alpha as that fraction, then the w must be orthogonal to vector u. Okay. So now then this is called the orthogonal projection of y onto L, and then denoted by this. Okay. All right. So next one, um, let's see. Let's see example. 3. So let's say y is 7 to 6, 7 and 6, just 2 by 1 matrix. Vector u is 4, 2. Okay. Define the orthogonal projection. The question is define orthogonal projection J of vector y onto vector u. Then write y as a sum of two orthogonal vectors. Okay, so let's see. Then write the sum of two orthogonal vectors. And then the orthogonal vector 1 in span u. Okay, u is vector u. Okay, and 1 orthogonal to u. So here's a solution. So yeah, let's find a projection first. The orthogonal projection of vector y onto vector u. This is equal to what? Y bar, then u, dot product of y and u, and then u dot u, right? Then y dot u is what? So right here, the y dot u is equal to, what's that? Y bar transpose, right? Vector u. Okay. This is a matrix multiplication. Okay. That's the inner product. Okay. Yeah, so this is a 7 and 6, and then 4, 2. So 28 plus 12, this is 40. And then u dot u transpose, and then u, right? So 4, 2, and 4, 2. 16, 4, which is 20. Okay, so 40 over 20, right? Which is 2. Okay. So now, next question is to write the sum of two orthogonal vectors. One in span u. Yeah, write the vector u y as sum of two orthogonal vectors. One in span u, and then one orthogonal to vector u, right? This vector u. So we got the orthogonal projection, right? Onto vector u, right? So now it means that this is gonna be r power, right? That is equal to r power. So here's a vector u. Okay, vector u. Okay, and then here's a. I think this is vector u to u, and then r power 2 times u. Oh, that's too long. Maybe this. This is a 2 times vector u. Now 2 is what? This is r power, right? And then maybe back to the vector y is right here. Okay. And then we want the problem asks you to write vector y as a vector 1 in span u. What is span u? Span u should be line, isn't it? So give me a second. Yeah. This gonna be, let's say, line L. That is gonna be what? Span. It's a u, right? Isn't it? So yeah, and then anyway, so this is a w right here. W. But we know that w must be what? Equal to y bar minus what? 2, I mean r by u, right? Isn't it? That is equal to, so w bar is equal to what? Y is what? 7, 6, right? The 7, 6 minus alpha is a 2, and the vector u is a 4, 2. So that's going to be minus 1, right? And then 2. That's a w. So vector y is equal to negative 1 comma 2, now plus alpha u, which is 2 times u, which is 8 and 4. So that's a w. That's alpha u. Alpha is 2. Okay. So all right. So yeah, I expressed the vector y as a sum of two vectors. One in u, one is orthogonal to vector u. Okay. So this is the w. Okay, this is w. All right. Okay. So please refer the figure in the textbook for this one. Okay. So now give me a second right here. Next one is orthonormal set. Okay. So especially the all of vectors in the orthogonal set, their the magnitude is 1, then we call that as an orthonormal set. Okay. So, it's orthonormal set. Okay. A set U1 through the UP is an orthonormal set. Orthonormal. Set. If yeah, it is orthogonal set of unit vectors. So magnitude is 1. That means each vector is the unit vector, right? Oh,